get into some terminology. Now, these are things that I thought were very important to understanding really the mid-range line from an EMC perspective. Now, some of this stuff can be applied to other vendors as well, but it really is applied to EMC, and you'll see that some of these things are really common to EMC themselves. Now, defining an active-passive array. When you think of, at least from the Clarion perspective, if you ask anybody from EMC, they may say that, really that active-passive terminology went away when the CX, went away and the VNX replaced it. It's hard to say that. Active-passive is really not as easy to define as you would think. Sometimes it's seen as a negative, sometimes active-active always gets all the glory because, especially in situations where you have failed components, that's really when active-active pays for itself, because you're able to provide the same level of performance even though you've lost maybe a hardware component. With active-passive, if you lose one of your major heads, one of your SPs, you're going to suffer. Okay, it's not common for you to have LUN ownership, all your LUNs sitting on a single SP. Usually it's balanced across your SPs. So if you lose a single SP, well, now you're at 50% performance, right? That's not common on the higher end arrays, so it does get sometimes seen as a negative. Now, LUN ownership in itself, when you go out and you create a LUN, and that LUN is really the raw data that you're handing up to your host, and then your host puts a file system on it, that LUN ownership is only owned and serviced by one SP at a time. All right, that is the simplest way to state an active-passive array. Right? You have LUN ownership, it's owned by a given SP. That means your host is actually transmitting I/O across one SP at a time. Now, when you add in something such as ALUA, asymmetric logical unit access, this really changes the way how active-passive operates. But does it really? I mean, LUN ownership is still defined to a single SP. So with ALUA, the best way for me to describe this, and this is a very common diagram when it comes to ALUA itself, it's not something that I developed, but if you look at it from this perspective, if I have a host, he's sitting at the top, and I have my big blue LUN at the bottom, normal access would be that far double arrowed line off to the right there. So the host would hit SPB, and then SPB owns that big blue LUN, and that's how he's accessing. He's going through his paths that are allocated through SPB. Now, if you lost SPB just died. In normal situations, without ALUA, any LUNs that were owned by SPB now get failed over to SPA. And you'll see the host itself actually has access to both SPs. Okay, so that's to give him the ability to access that big blue LUN across either SP in case one of them dies, so it's not a single point of failure. The double-headed arrow on the left-hand side is how ALUA would access that big blue LUN if for instance, say SPB lost some ports that the host was accessing that big blue LUN on. So it doesn't really help you, and this is kind of mentioned down here on the third bullet point. ALUA doesn't help you if you lose an SP in its entirety. There's no benefit with having ALUA in place. The benefit comes when you lose front-end connectivity to SPB in this example. Then the host can access that LUN that is owned by SPB via SPA across that interconnect, that internal messaging interconnect between A and B. So its path to that LUN is really host to SPA, from SPA to SPB, then down to LUN. So LUN ownership never changes hands with ALUA in play. You lose an SP, doesn't matter. You lose B, everything trespasses or moves, migrates, whatever you want to call it, over to SPA. Now that host is accessing that big blue LUN across SPA. That's how it works. Now, there's this notion within ALUA of optimal and non-optimal I/O transmissions. Okay, so optimal access to that big blue LUN would be across SPB in this example. Non-optimal would be across SPA. So that's a very common terminology with ALUA itself, optimal and non-optimal pathing. You actually see once we get into the interface within the lab itself, it actually says optimal and non-optimal. It shows you that information within the GUI itself. Symmetric active-active, so SAA, This would be AAA array. So a typical VNX would be an AAA array. This would be a Symmetrix or VMAX would be a SAA array. That's able to provide active-active connectivity to a LUN at any one time. So it's actually able to traverse multiple controllers or directors and get access to that LUN on the back end, that big blue line, right? And this just gives you increased throughput. It also gives you the ability to sustain the performance that you were used to prior to that component failure if you were to lose a hardware component or a director or whatnot. So what I want you to take from this slide is that EMC markets the VNX as an active-active array, but it is an asymmetric active-active array. And what makes it asymmetric is a Lua, is the Lua failover capabilities. But to me, it still is an active-passive array. That LUN is still owned by a single SP at a time. So what's the front end? The front end, you should know what the front end is. It's really the conduit between your host and your storage array. Now these are all controller based. They're copper and fiber channel ports, and on those ports, they're able to process common data center protocols. Right, so you've got, you're able to read, if you've got fiber channel ports, you're talking fiber channel across those fiber channel ports. If you've got iSCSI ports, you're talking iSCSI across those copper ports. Same with FCOE. The front end ports itself are handling incoming data from your host, and they're handing them off to cache. Cache is going to be their first dumping ground on the array itself, and then that acknowledgement is sent back to the host. Then over time, that data in cache gets destaged, what's called destaged, to the back-end disk for its, kind of its final resting location. So we want data in cache. The more cache you have, it's typically better. And that's why you see things like fast cache that come into play that allow you to utilize your EFDs for a secondary cache tier, because we want data in cache. It's going to be received and accessed a lot quicker than a mechanical spinning disk. The back end, this is the conduit between cache and your physical drives. This is the SASN bus transport that's between your SPs and the DAEs themselves, or your disks themselves. This replaced the fiber channel arbitrator loop of previous arrays on the CX line. I mean, it really is ridiculous on how fast it is in comparison. Huge improvements from previous generations. Much needed change. Fiber channel arbitrator loop was simply not capable of handling a lot of the new disk technologies coming in. So SAS backend bus is certainly capable of that. From a backend perspective, you're doing error detection, soft errors, hard error, media writes, things of that nature, error correction, and all your rating takes place on the backend as well. Now the vault drives, the vault drives have been around for years. So ever since I've dealt with EMC mid-range arrays, the vault drives have always been in place. It's just a common building block. It's just the way the arrays are architected. On the 5100, the 5300, and the 5500, which have, if you remember correctly, have the DPE, right? So it's really the collapsing of the SPs and the first DAE into one enclosure. On the DPE, your first 4 drives would be your vault drives. Now on the higher end arrays, the 5700 and the 7500, where you have an SPE, the vault drives are not included in the SPE because there is no drives in the SPE. Right? Your first DAE is essentially DAE 0. It's enclosure 0. Your vault drives are going to be the first 4 drives in bus 0, enclosure 0 on the higher end arrays. This is an area reserved for the operating system. It's where VNX-OE for block lives. It's also where the cache vault lives. Now what the cache vault provides is a D-stage area for your hot data, your cache, in case of power loss on the array itself. So you have data that's coming in from your host, and it's coming across multiple protocols, maybe on, especially on the SPs. If it's coming across as FCOE, iSCSI, or fiber channel, that data is always going to be written to cache first in most scenarios. At that point in time, if you lose power to the SPs and the array itself, you have a finite amount of time where that data in cache needs to be written to disk. And that's where the cache vault comes into play. That's where it has enough capacity where it's able to write the data that exists in cache, which is going to be all your hot data. It has enough capacity to be able to write that data to the cache vault itself. Now, with the vault drives, I didn't mention earlier, but with the vault drives, 192 gig off each disk, each of those 4 disks is consumed for these capabilities, both the operating system and the cache vault itself. Now, there's some other things in there as well that I haven't mentioned that I won't get into, but I wanted to mention those are the two providers of what the vault drives give you. So just keep that in mind. You are losing capacity on the first four drives, and normally you would not put any data on the first 4 drives for a number of reasons. But as you add more things that may be more I/O intensive on the vault drives themselves, could it potentially affect the performance of the array. So you really want to keep things off of there unless they're pretty stagnant. I've commonly used them for ISOs, data storage within a VMware environment, also templates. A lot of the times, maybe it's a pretty stagnant environment as how much you're deploying within your data center. You may want to put those template data stores, those ISO data stores on the vault drives themselves. Also, your control LUNs for your data movers themselves will go on the vault drives typically. Storage groups. This in short is LUN masking. I'm saying I have a LUN and I want this LUN to be seen by these particular hosts. That's it. Everything else, I don't want to see these LUNs. Why would you do that? Well, do you want a Windows host to be able to access a VMFS volume on the VMware side? No, you do not. And there's a lot of, there's, all these operating systems typically may have different types of proprietary file systems that they use. So you don't want a system that's outside of that OS to be able to access a file system that it does not recognize, especially from a Windows perspective, because it will grab that LUN, it will just interrogate it, and it will just do things with it that you don't even want to know about. So that's why we have storage groups set up. Okay, so it's for this LUN masking capabilities. Now, it's a feature that allows LUN access to some hosts and disallows access to other hosts. Now, one common thing with storage groups is that a host can only live in a single storage group at one time. So you couldn't take an ESXi host and put him into multiple storage groups. The flip side to that is that you could take a LUN that ESXi host and sees and put it into multiple storage groups. A common scenario over this would be boot from SAN LUNs, in Blade environments, where each boot from SAN host needs to see and only see its boot LUN for booting up. It's got the operating system on that boot LUN. But you don't want any other host to see that boot LUN. But you do want to give every other host or all the hosts access to common shared VMFS data stores. So how do you do that? Well, on the VNX side, you would have a storage group for each host. And in that storage group, you would have a single boot LUN that only that host can see, but you would have all the VMFS shared data stores across all the storage groups. That's very common. We see that a lot nowadays. And that's really how you do it. It's not that we've come up with that or anything. That is how you do boot from SAN LUNs, in particular with Blade servers. So defining traditional RAID groups. This is what EMC's been doing for years on their block arrays, right? It's just you're pulling together or grouping together disks, up to 16 disk increments, and you're applying array technology. Now, usually there are preferred discounts within certain RAID types. They have what's called 4+1s and 8+1s. These are common RAID groups for RAID 5. There are certain discounts that you would want if you're doing one particular RAID group over another. The RAID groups that are supported on traditional RAID groups are 0, 1, 10, 3, 5, and 6. Now, the max number of disks you could put into a RAID group is 16. You'll see this is vastly different on the storage pool side. We'll see at the next slide, is that you have a finite amount of disks, a very small number of disks that you could put into a RAID group itself, but you do have the ability to do isolated type setups where if you wanted to go in and you wanted to create a RAID group just for transaction logs for a single SQL server, you could do that and not burn up a lot of space, and certainly not have that in a shared environment such as storage pools would offer. So there is very much a common use case for traditional RAID groups. For the longest time, we were using traditional RAID groups for things such as journal volumes on recovery point and things of that nature. There's also other scenarios you would use traditional RAID groups, so don't completely discount them in your designs. Know that they are there to provide that isolated performance in situations where you need it, where it doesn't, maybe a LUN doesn't serve best in a traditional storage pool environment. All this talk of storage pools, what are they? You have file and block storage pools, and you'll see this once we get into Unisphere. You do have the ability to be able to carve up storage pools from the block perspective and create LUNs on it. And then you do have the ability to create storage pools on the file side and create file systems on it. Now, to add another layer of complexity to that, you also can create storage pools, create LUNs on those storage pools, then push those LUNs up to the data movers themselves, create another type of storage pool, and then within that storage pool on the file side, create file systems. So you can do that as well. A lot of different layers of abstraction, if you will, to be able to accomplish that, but certainly very prevalent in our customers' environments today. Pools are just a bunch of disks with applied RAID technology, right? So with traditional RAID groups, we had a set number of disks that we could provide in a traditional RAID group of 16, the max. With storage pools, you can provide hundreds of drives within a storage pool. Now, some of those numbers depend on the models that you're running these storage pools from, so that's why I didn't put in an exact number there. But just know it gives us the ability to pull together disk, apply RAID technology, and it is much larger than a traditional RAID group. Now there's these what's called private RAID groups and LUNs that really underpin these storage pools themselves. For instance, if you had a 10 disk storage pool, you would have a private RAID group. You would have two private RAID groups. If this is a RAID 5 storage pool, you'd have two private RAID groups, two 4+1. So that's commonly how a RAID 5 RAID group is referred to as a 4+1. You have 4 disks for data, one for parity. It's just the common technology in the storage, or a common terminology in the storage world. So you would have two private RAID groups underpinning that 10 disk storage pool. Then on top of that, and this may have changed in FLAIR 32, but on top of that, you would have private LUNs that are actually created on the fly or on top of those RAID groups, those private RAID groups. And then that capacity is served up into the interface, and then you create your data LUNs on top of that storage pool. Very confusing process. It is how storage pools themselves are architected. Multiple RAID groups in VNX OE 32, you now can have multiple RAID types within a storage pool itself. That was just not common in anything prior to 32. When you define the storage pool itself, you define the RAID type at that time. If you want to do FAST, which is fully automated storage tiering, you have to be in a storage pool itself. You cannot do this across traditional RAID groups. We do all of this, why? So we can create LUNs. If you're talking storage and you're talking block storage, you're talking about the LUN, and that is really the logical construct that we decide the capacity of that LUN based on the pool that we're creating that LUN out of. So we may have time space within a pool or a traditional RAID group. We're carving up the size of the LUN based on our requirements from a host perspective. And like I said, it is a logical construct. You do designate either one or multiple disks underneath with an applied RAID technology. This is central to block-based storage. When you talk about block-based storage, you talk about LUNs. Now, the compression and deduplication, at least compression is applied on both sides of the array, meaning both file and block perspective. Now, these are space efficiency technologies. Compression is available on the block and file side. Deduplication is only available on the file side of the VNX. So keep that in mind when you're designing out there. Both of these operations occur when data is at rest. So if things haven't been accessed in a set amount of time or they haven't been modified in a set amount of time, that's when you would apply compression and deduplication. It's usually not for hot data out there. This could impede the performance if that data is compressed and it has to decompress it as part of an operation that a host is trying to access that data, or even deduplication. If you are accessing data that's been deduped or compressed, it could be a bit of a delay for doing that. So you do want to make sure that is occurring data that is at rest and not frequently utilized. It is an asynchronous operation. It's only available on the 5300s and above, so it's not available on the 5100. So what's a hot spare? A hot spare is global in nature and it allows you to protect a failed drive of equal size or less across the array. So if you have a 3 terabyte nearline SAS drive, you have to have a 3 terabyte nearline SAS drive hot spare to be able to protect it. If you have a 3 terabyte nearline SAS drive that is a hot spare and you lose a 2 terabyte nearline SAS drive, then that 3 terabyte nearline SAS drive can protect the 2 terabytes. So that's what that statement is saying. Another component of that is that if it has to be the same drive type. So you couldn't have a nearline SAS drive hot spare a SAS drive. So therefore you have to have a hot spare for every drive type. You have to have a hot spare for your largest capacity drive within that drive type. And then the normal rule of thumb is to have a hot spare for every 30 drives in your array itself. So those are some of the design aspects when it comes to hot spares. Now, what does a hot spare do? It assumes the identity of the failed drive. In parity RAID types, the data is rebuilt on the hot spare from the surviving drives. For mirrored RAID types, data is copied from the survivor mirror member to the hot spare. Now, when you replace that failed drive, things kind of take place in reverse. Data is copied from the hot spare to the new drive, and then once that's done, the hot spare is returned to a normal idle operation and therefore is able to serve out or hot spare other failed drives. So hot spares, I believe are common across most vendor arrays. The VNX is no different, but certainly something that is desired. Don't configure your production arrays without hot spares.